vectors here. And we're going to start out with a word problem and looking at our vector. So in this case, we've got a soccer player that gets the ball at a 10-meter line, dribbles the ball down the field at 5 meters, then passes the ball 5 meters across the field, and the opposing player intercepts it and actually goes down 20 meters. So what we've done is we've described the motion that's happened. So our first soccer player went down the field 10 meters. And then he passes the ball to the second soccer player, and this is 5 meters. So this is in meters, this is in meters. And this person ends up taking it back this direction, 15 meters. So all I've done is like that traditional, I'm walking in the blocks and I've got my individual vectors. So these are one-dimensional vectors, and they're only traveling in one dimension, but I can add vectors head to tail. So just by looking at this description, we know we can add our vectors and we've got something that's there. Now, what we're asking is the displacement. So this is really the thing that we want. This thing in red is our displacement. And our displacement now happens to be in 2 dimensions. We gave our description here in 1 dimension, but now we happen to see it in 2 dimensions. Now, what's interesting here is we can actually get this part because we can use our geometry to get our trigonometry. We know that this is 5 meters. And if we came back 15 meters, we know that this section here is 5 meters. And we can actually get that part there. And so we know that in order to find my displacement, c squared is equal to a squared plus b squared. And this is 5 squared plus 5 squared is going to give me 25 plus 25, which is going to give me 50. And so c is going to be the square root of 50. And if I go ahead and calculate that, that says that this is 7.07, and this was all done in meters. So the length of this vector is now in meters. So we've answered the question, but we can do it a couple of other ways as well. For example, I can rewrite these vectors. So I can have vector A, and this is traveling in the negative 10 meters in the I direction, as how I've drawn it. I can have vector B. This is traveling in the negative 5 meters in the J direction, because this is in the I direction. Remember, I is a unit vector in the X direction. J is a unit vector in the Y direction. So now I've got that. And I can have vector C, which is now a positive 15 in the I direction. I can add these vectors in our vector notation. So what I'm going to do is I'm going to rewrite this to make it make a little bit more sense. And I've got a negative 10i. I have a minus 5j, and I have a 15i. But there is no j, and so I add all the i's together and I add all the j's together, so I end up with a positive 5i minus 5j gives me my resultant vector. And we've done that visually right here. I'm in the negative y direction, but I'm in the positive x direction. So now I've represented my vector in this notation, telling me that I am going this direction here and that direction there. And now I can calculate the magnitude of this. vector, and that is just the square root of 5 squared plus my minus 5 squared gives me my square root of 50, and now I get my 7.07 meters. So I can come up with it in just the exact same way. I can come up with it in just the exact same format. The other thing is if I want to find an angle here, so I want this angle, well, because we know that that is a right triangle, we probably can guess what the angle is, but basically what it's going to be is the tangent of the angle is going to equal my y component divided by my x component. And I think when I answered someone's question in WebAssign, I think I have them flip-flop, but you're going to do the arc tangent. So in this case, my y component is a negative 5, my x component is a 5, and this is the arc tangent. So if I do that, this will be the arc tangent. So I'm going to do the inverse tangent of 1, and actually this is going to be the inverse tangent of minus 1. And that tells me that this is a negative 45 degree angle. So this will give me a negative 45 degrees. And that's telling me that that's this angle right here in my picture. So as we start working with these vectors, understanding our components make a lot of difference. So that's one way to do it. So let's look at vector notation a couple of different ways. So I'm going to start with a vector A, and I'm going to give a vector A as in 3i minus 6j. I'm going to get a vector B, which is 6i plus 2j. And I want to know what A plus 2B is equal to. Okay. Now I can do that a couple of ways. So I'm gonna actually draw my vector A. So I'm gonna start with this point here on my paper. I'm gonna use this. We're gonna add them head to tail here. So this is plus 3. So I'm gonna go over here. So I'm plus 3. And now I'm going to come down 6. So this is 1, 2, 3, 4, 5, 6. So my vector A looks just like that. Now I'm going to add vector B head to tail, but I want to add 2 B's. So we're going to go over here. We're going to go 1, 2, 3, 4, 5, 6, but I go up 2. So there's 1. And I'm going to do the same thing. 1, 2, 3, 4, 5, 6, up 2. 1, 2. So this one is B, this one is B, and this one is A. The resultant vector is going to look something like this. This will be my resultant vector. And if we actually look at this and we can take it off of our chart here, we know that this is 3 plus 6 plus 6. So I get 3, 6, and 6. That's going to equal 15. And then I went down 6, but I added 2 and I added 2. So I'm at minus. So this is now down here at minus 2. So we did it graphically, but we can also do it algebraically, where I'm going to take A is equal to 3i minus 6j. I'm going to write 2b, which is going to be 6i, because 3 times 2 is 6. 2 times 6 or 2 times 2 is 4, j. Now I'm going to get the result. Did I do that right? Oh, I didn't do this right. This is 2 times 6, so that's 12. This is 2 times 2, so that's 4. So we're good there. So I've got 2 times 6 is 12. So I've got 3 plus 12 is 15i. And I have minus 2j, and that gets me my resultant vector. If I want to know the magnitude of that resultant vector, that is going to be the square root of 15 squared plus minus 2 squared. I get 225 plus 4. Gives me the square root of 229. Gives me 15.1, whatever these units are. So that's 15.1, and my angle would be the arc tangent of minus 2 divided by 15. Gives me a negative 7.6 degrees. That looks about right. That looks a little bit like less than 10. So there's our angle that we just calculated. So if you do the negative, you're going to use that same thing on the negative. So let's kind of just do a couple of them. So if I have negative 3a and a is equal to, we'll go ahead and keep the same a that we just had. Negative 3a would equal a negative 3 times 3i. I'm going to do it this way just so that we have it nice and clean. So this would now be negative 9i plus 18j. So you can do vectors a variety of different ways, but mainly you can add them head to tail, and we can work through them. We can do them graphically. We can walk through the individual parts. We can do them using this kind of notation. And that starts getting us into how we deal with two-dimensional motion. Because when we're starting to deal with 2 dimensions, I can look at a problem like this. So we're going to have a rocket here. And we're going to send off our rocket and have it travel at 50 meters per second for 10 seconds. And we're going to give ourselves an angle here of 33 degrees. And what we want to know, and we're starting from rest. So our initial velocity is equal to 0, our 50 meters per second for 10 seconds. And we've got it coming off here. So we're just looking at, we've sent this off on a rail here. So we're just going to worry about that travel. And we want to know what the range is. All right. So we're traveling for 50 meters for 10 seconds. So we know this is going to be this angle here, or this distance right here. That distance is going to be 500 meters, because that's the velocity times time And we said that we were traveling 50 meters per second for 10 seconds. So that gives us that. But we're now at that 33 degrees, and we want to know that range. Well, we know that the cosine of the angle is going to equal the adjacent side divided by the hypotenuse. So this is going to be the hypotenuse times the cosine of the angle is going to give us our adjacent side, which in this case is the range. So now we know that that's going to be 500 meters, cosine of 33 degrees. It says that we traveled 419 meters, but now we want to know how high we are. Do the same thing, except now we want the sine of the angle. So this is going to be our 500 meters, sine of 33 degrees. We're going to be at 272 meters if we're dealing with this part right there. So that's kind of why we want to be able to convert from one dimension to two dimensions, because the thing about it is that we're about to see that our motion, so if I'm in a car and I am tossing a ball directly overhead, my view is going to look like this. If I'm in a car, and even though the car is moving along that way, if I toss the ball up, it's going to come right back down and hit my hand. But if I'm a person that's looking outside and the car is moving, the ball is going to look like it's traveling like this, because it's got the motion of the car, and it's got the fact that it's had an initial x velocity, but it's going to look to me like it's going like this. So this is showing that the x direction is independent of the y direction. And that independence is going to come into play when we start talking about projectile motion. Which we're going to talk about on Monday. Okay, questions that have come up about vectors?
I had a question on the first picture with the triangle.
Yep.
With the red line. On the vectors.
Yep.
Not this one, but actually the next one.
The next one. Oh, you want this one?
Yes. So when you started the drawing up top, why did you go 3 to the left but not to the right? Because that's like a positive 3.
Right. It went through. Yeah, it went 3 here. 1, 2, 3. But we're going, this is in the x direction, and that's in the y direction. So you could go down 6.
Okay, so it didn't matter whether you went to the left or the right?
Well, this is the positive direction. So my 3 is positive.
Right.
But on this one, it didn't matter.
Okay.
It's just however I did my drawing. This is, I could have reversed this one. Okay, I could have reversed this one because I didn't say this was on the red side or the blue side. So I could have done that one the other direction. as well, because I didn't specify which direction was positive.
All right. Also on that same picture that we were talking about, the bottom, the last step, because I like the algebra way. I think
Yeah.
that will work better for me on these sorts of problems. But I had a question about the -2 on the very bottom. Why is that -2
Well, this is
on the?
-6 plus 4.
Okay.
And that, you know, when I add those together, I get -2.
Oh, you just put okay. That makes sense. I see it now. You got.
Yep.
I was only looking at the 15.
Yep. Nope. There's a -6 up there.
Okay.
Hey, other questions? All right, I'm gonna stop recording.